Hello, welcome to the lesson on interference in an air wedge and single slit interference. So I've put these two together and kind of deal with them separately. You can watch the video, the first part of the video on the air wedge, and you have enough work done for the following day, and then you can watch the remaining video or videos with the single slit interference. It's kind of two topics, but the air wedge, I find I can go through it quickly, and a lot of times it doesn't take long to do the homework, so you can kind of plan it out. So your goal today: determine the interference patterns that develop from an air wedge and from a single slit screen. So we're going to look at the air wedge first. That's our first goal. So in front of you, in your note, you have this crazy looking drawing to start with. And I'm going to clarify some of the information. I just gave you lots of the details already. So what we have here is basically a piece of glass and another piece of glass that is separated by some thickness T. So I'm going to put just to make that a little bit larger for you to see. And in between here, we're going to have some other material. So it could be air or water are the two common ones. We can put oil in there. So I'll just put etc. So you put some kind of liquid or gas in between. Okay. Now, the reason for this separation of this thickness is that a hair or string has been put in between or put at the end. All right. So this is definitely very exaggerated because this actual distance T is going to be very, very small. Okay, it's only going to be the diameter of a hair, a diameter of a string, diameter of a thread, something very, very tiny. So it's obviously, we've zoomed in quite a bit. So let's talk about what we're looking at here. We are analyzing light rays that are coming in. So we really have two light rays coming in, light ray 1, light ray 2. From the previous lesson, we talked about different outcomes that can occur. So outcome 1, I'll do this in a kind of a highlighter pen, it can travel through the glass and then reflect, okay, and refract out, or it can refract, transmit, reflect off the bottom glass, refract, transmit, and exit. All right, so there are those alternate paths. So we're looking at what's happening with light that gets reflected in the back of the first piece of glass, and how does that affect the light that gets reflected off the back piece of glass. All right, so what we're going to do then is look at this length here, the distance from here to here. We're going to let it be lambda, so one full wavelength. And proportionally, we are going to say that this length here is lambda by 2. All right, so we're picking two distances here that allow us to do a bit of an analysis, come to a generalized equation, then it'll take care of all the other equations for us. So what we end up with is two similar triangles. So we have triangle number 1, my yellow, and then we'll have triangle number 2, which I'll put in green. Just go outside a little bit. So here are my two triangles, and they're both similar triangles. All right, so if we go then to kind of set up the equation here, we're going to set up the equation, but what I want to do is I want to incorporate the value of t into it. So there's actually a third similar triangle, and that is the larger one. All right, so we got 3 similar triangles in reality here. So what does that tell me? Like I said, I want to incorporate or tie everything back to the value of t. So the first triangle, the base length here is x1, and this length is y over 2, or lambda over 2. So x1 over, now my teal triangle, the outside one, has a base length of L, and I'd have lambda over 2 compared to the thickness of the slit. So there is my first relationship, or just first similar triangles, just using grade 10 similar triangles. Moving to the green triangle and comparing it to the teal one, I would have x subscript 2 compared to the length. That's equal to lambda over the thickness. There's my second relationship we're going to link together. All right. Now for both of those, I'm going to rearrange it. So now I get to do a little bit of algebra. The first one I'm going to solve for x1. So x1 becomes, the L will get multiplied to the lambda, and the 2 really moves to the denominator mathematically. So it becomes x1 is equal to L lambda 2t. Similarly, x2, I multiply the L up, so we get L lambda over over t. Now, what I want to look at is I want to look at the difference in the x value. So I want to calculate delta x. So delta x is simply x2 minus x1. We know that x2 is L lambda over t. x1 is L lambda over 2t. I'm going to common factor out an L, a lambda over t, and that would leave me with 1 minus 1/2. And when you simplify 1 minus 1/2, that's just 1/2. So we end up with delta x is equal to L lambda over 2t. That's 1/2 times that fraction. So there is one of the equations you want added to your cheat sheet. Okay, and that's really one of the main one that we're really looking at here. So off to the side here, give ourselves a bit of a legend. So where delta x, what we just calculated, is the bandwidth. And just to clarify that, up above here, if we're looking down from the top here, so top view, all right, so if our eye is up here, and we're looking at the resulting pattern on the wedge, it really looks like here's the glass plate that's elevated. What you're going to end up with is similar to our double slit refraction, where you'll have right band, constructive, destructive, constructive, destructive. So that distance in there, from here to here, that's your delta x. So it's that bandwidth, how wide is the constructive interference. All right, L is length of wedge. T is the thickness creating the wedge. All right, so the diameter of the hair and whatever. The lambda is your wavelength. All right, so that gives you the general equation, and that's really all there is to deal with when you're talking about the air wedge. So we're going to show you an example, some of the other factors that come into play, but for the most part, those are the only equations that we're really worried about. So in this example, the air wedge is made of 2 glass slides, 11 centimeters long. So I'm going to pick out some of that information right away. So again, working in SI, 11 centimeters is 0.11 meters. Separated by the end, so what they did is they put a piece of paper between the glass right at the end, and the thickness of the paper is 0.091 millimeters. So we're going to have to divide that by 1,000. So that means that, I guess, 0.091 millimeters, that's equal to 0.123091 meters. We're going to answer the following. So I guess we're heading into part A. If red light, so now we know lambda, it's given information, 6.63 times 10 to the negative 7th meters is shown on the wedge. What is the spacing in the interference pattern between dark fringes? So it really doesn't matter, bright fringes, dark fringes, it's the same formula. So we are looking at determining the bandwidth here. So we have the formula, L lambda over 2t. So from the previous side there's my length. Lambda is up above, divided by 2 times my thickness. And when you calculate that out, your calculator is probably going to give you this, which is 0.44 or 0.4 millimeters, would probably give you the answer in the back of the book. So therefore, the fringes are going to be 0.4 millimeters apart. So actually this one's pretty tough for you to detect with the naked eye when the bands are that small. All right, B part. How would the spacing change if the air wedge was filled with water? So remember I said between the air wedge, so here's my two pieces of glass, the medium in there can be a couple of things. So we assumed air for the first one. So now in B part, we're going to put water. So the only thing that really changes for us is that lambda is involved in this equation. So we need to figure out, well, what's the wavelength of light when it enters water? So this is when you got to look back on your formula sheet and find that equation that tells us or calculates our new wavelength. So that's a comparison of our indices of refraction. So 1 over 1.33 equals the new wavelength over 6.63 times 10 to the negative 7. Doing my calculation for lambda 2, we end up with a wavelength of 4.98 times 10 to the negative 7. And that's in meters. So the wavelength decreases. That makes sense because your velocity is going to slow down inside that medium. Now it's just a matter of recalculating your delta x. Lambda over 2t. So 0.11, 4.98 times 10 to the negative 7. And 2 times your thickness, 0.1291. And when you calculate that out, again, the calculator will give you 3 times 10 to the negative 4 meters, which is 0.3 millimeters. All right, so what that does then, if we were to change the medium, in this case, putting water in there, it's going to decrease the bandwidth. So therefore, bandwidth decreases. All right. So as I said before, that's enough. Even though the lesson continues on, if you have time, you can finish this lesson, but it's really 2 lessons. This one's just a very short component, so that's why I kind of tie them together, or traditionally have tied them together. So technically, you have enough work for tomorrow by the time you do the homework and do the journal. You have enough information at this point in time to keep busy. However, if you do have the time, you want to finish this off, you're going to have 2 days worth of homework available to you. So anyhow, I'll continue on. This concludes the example and similar examples you're going to have with the wedge interference patterns, and we'll finish off the last video or two with the single slit interference.